Compilers are programs that convert nice, human-usable source code and convert it into seemingly obfuscated machine code. While this process of making one of these programs may seem difficult on paper, it's actually easier than you think. That's why today I will show you that writing a compiler is not as difficult as it may seem. For starters, we must pick which kind of computer our compiler will compile to. The human-readable, computer-specific machine code emitted by compilers is called assembly. Not all assembly languages are the same. Although assembly is a human-readable version of machine code, don't think that writing assembly is as high level as writing C. Everything written in assembly happens one-to-one on your system, but it's just that assembly is easier than filling program headers manually with hexadecimal bytes. There have only ever really been two types of architectures that a CPU can fall into, not including the switches and punch cards that came before them, those being Intel and AMD's x86, a CISC architecture first introduced with the 8086 microprocessor in 1978, and ARM, a RISC architecture first introduced on Acorn computers in 1985, that primarily runs on Raspberry Pis and Macs. Because of how there are more Intel and AMD computers out there than ARM-based CPUs, I will be using x86 on a 64-bit system in this series. Assembly languages also differ from OS to OS. Well, not in terms of machine code. That still runs the same. However, there is an ABI, Application Binary Interface, that sets standards for the way programs interact with the kernel. For example, if you want to write something to the console, which is called standard output or stodout, this will be done with a system call interrupt on Linux, but a regular function call on Windows. In their effect, both of these solutions are pretty similar, but I will be using Linux throughout this series. Lastly, there are different flavors, or syntaxes, of x86, most prominently called AT&T and Intel syntax. The syntax of assembly varies from assembler to assembler. For example, NASM, the NetWide assembler, uses Intel syntax, while the GNU assembler, or GAS for short, which is included in GCC, uses AT&T by default. For this series, I'll be using GAS and AT&T syntax, because a copy of GCC comes with every installation of Linux. Now that we have that out of the way, I think it's time to tackle the first step of compilation, called tokenization. As the name suggests, tokenization will convert a bunch of letters in a file into tokens that can be analyzed and used later, which is much easier to deal with than the raw characters yourself. The part of the program that does the tokenization is called the lexer, and we will start writing this now. This stage of the compilation is pretty easy, so I will show you a basic working example of one in C++, although the language you use to write your compiler in is subjective and doesn't really matter. Let's start by making a main function that reads the file included in the arguments of the program and put it into a string. Next, we can create a lexer class with a tokenized function that returns a list of tokens. In this tokenized function, we can create a while loop that loops over an index over the string. We can start with white space, which we can simply skip over. Next, we can check for one character wide tokens that are pretty easy to check for. For example, those can be colons, commas, periods, ampersands, brackets, etc. Those are pretty boring. So what about numbers and letters? Here we will check if the current character we are analyzing is a digit. If so, we will append digits to a buffer until the current character is no longer a number, after which we can push the buffer as a new number token. If the current character is a letter, however, we will do basically the same thing, appending characters to a buffer until the current character is no longer alphanumeric, or underscores if you choose to allow them in your language. Lastly, we have to remember to return the list of tokens we created and pass it back to the main function so it can be parsed. Parsing is the most fun and the most annoying part of compilation. In the parsing stage is where you define rules for the syntax of your language. There are nearly unlimited ways that you could declare a variable, but the parser is where you can define what they should look like for your language. There are also different kinds of parsers, including iterative and recursive parsers and Pratt parsers. There are many tutorials out there for how to implement both types, but there are a few concepts you should understand. All elements of your language will fall into two categories: statements and expressions. Statements make things happen, while expressions return values. For example, variable and function declarations are examples of statements, while a binary operation like addition is an expression. After you've made a parser, you can optionally include a stage called typechecking, where expressions are analyzed and checked to see if their value matches what is needed, like passing an argument into a function. The type checker can also assign inline types to expressions, which can be helpful later. You may also want to include other stages to your program, like macros in C. This stage is pretty boring, and I personally don't like using macros, so I will not be showing you how to implement these, but you can if you want to. Last but not least, you have reached the codegen stage, where your program full of statements is converted into assembly before it's shipped off for use. Because this video is basically just an introduction, I will only be showing you how to implement a basic exit program so you can get the feel for assembly. You may have made your program's method of exiting be a return from main, a function, a statement, etc. What you decide to use as an exit is up to you. After all, it's your language. In assembly, programs can only exit using positive integers that are 1 byte large. This means return codes can only be from 0 to 255, where 0 represents success and everything else represents an error code. In Linux, exiting the program is done with a system call, a type of interrupt that informs the kernel to kill the program, and free memory and stuff like that. All system calls use the RAX register to describe which call you would like to make. In the case of exiting, the syscall number in RIX is 60. Then you have arguments, which are passed into different registers for each one. In the case of an integer, the first argument of a syscall, which is the exit code in this case, is stored in RDI. Lastly, you must tell the system to actually make the call by using the keyword syscall. In order to move values into registers, you can use the code movq 60 racks. That may look kind of complicated, but it's really not. Movq, M-O-V-Q, means to move 8 bytes of the input to 8 bytes of the output. The reason we are using 8 bytes is, well, because the system is running on 64 bits. 8 bytes. The $sign before the 60 means that it is an immediate value, or a constant. The % before racks simply means it is a register. Not that complicated, right? Just repeat that for the exit code of your program stored in RDI. Make the system call, and assemble your output. Voila. Now your program returns 0. Pretty boring, but a good start. But how do we implement the integer value from the source code into this? You could try doing some strange interpreting and guessing, or you could do the simple way. And the simple way is usually the best way to get things done, so we'll go with that. In your program, when you encounter an exit, generate the code for the argument. When you find an integer literal expression, write push q and then a stringified version of the integer. Push q means to push 8 bytes onto the stack, which is a pre-allocated, readily available section of memory for your program to access. The stack is used for function calls, where the place to return is pushed on top, and when it is time to return, that value is popped off again. The stack is also used for storing variables and other things, but in this case, we're just temporarily using it to store the integer literal there. In order to retrieve this value, we must pop the top value off the stack by using the code popqrdi. As you may have guessed, this will pop the top 8 bytes from the stack and store it into the register RDI. Now you can place movq 60 racks and syscall, and ta-da, you successfully wrote a compiler. A very simple compiler, but a compiler nonetheless. Now that you've gotten this far, surely you want to know how to make variables and functions and other things now, right? Well, you're gonna have to wait for that, because now it's time to end the video. I hope you learned something new today. Come back soon for the next installment of writing the compiler, and please subscribe so more curious people like you can see the video and learn something new themselves.